short day, so we have to. I have to think about this. Perhaps I can make it something optional. For example, some extra practice stuff for people who want to come and practice some more, or something like that. Because as it is, it seems that we are missing 3 lectures on the 14th, on the 18th, and the 22nd, which is Saturday, but pretends to be Monday. We do have a lecture on the 20th, of course, which is Thursday. We are not missing that. So you have time to think until then.
Wait, 14th is Friday.
14th is.
What we miss?
I'm leaving on Thursday before the holiday. Let me see the calendar.
So the 14th is a Sunday.
No.
It's 15th.
December.
14th.
November, please.
Where am I looking? Okay.
November.
Okay, it's a Friday. It's Friday.
Okay. 7, 8, 9, 10.
Bring the old.
Okay. So yes. This week is okay. Next week is okay. The week after that is okay. The next 2 weeks are okay. No, they are not. On the 13th. The 13th of November is Thursday. So I'm leaving Thursday at noon. So unfortunately, I'm not going to be here for Thursday lecture. So the 13th. On the 13th, we miss our lecture. On the 18th, we miss our lecture. And on the 22nd, which is actually the 17th, or the 17th, was actually the 22nd, we miss our lecture because it's the short day. I'm not happy about having to miss out on 3 lectures, not because time is money, but because time is important. Time is knowledge. I'm away on Thursday the 13th. Then on Monday the 17th is moved to Saturday the 22nd. But the problem is that it's a short day. So we are missing that one. Now Tuesday, the 18th of November, is the holiday, so it's free automatically. So there's no hope for this. There's absolutely no hope for this. There's no hope for this to the extent that I'm simply going to be away. I'm not available.
What do you mean by short day?
Short day means that before the holiday, the working day is shorter than normal, and we are supposed to finish at 16 or 4 in the afternoon. And the thing is that because of that, we are going to miss that lecture as well.
But do you have time before the seminar or before it? Just in the morning? Do you have time in the morning?
In the morning, no.
When the holidays are starting?
Because I might have some time in the morning of the 13th, but probably not all of you have free mornings. Not all of you have free mornings. Not everybody will be happy at starting to start at 8:30 simply because. So I'm thinking about Saturday. I didn't know it's going to be a short day. Oh well, I should have known. I didn't think about it.
We have to.
Yes, it's going to be a short day. I will see. Perhaps I will not give any new material, but it will be a practice lecture. So those who want to come might come, because I'm a little bit afraid of being short of time in the end. I think the semester ends on the 20th of December, or 19th, well that's a Friday, yes. That's the week. At the moment, I'm not quite afraid that we might not have enough time, but you never know. You never know. That's life. Unfair, I know. So, the previous paper from last time, unfortunately, I don't have any extra copies because I took them home, as it seems, by accident. So let's have a look at the paper from last time. Fortunately, I have them in my Dropbox. All right. So state whether each function is odd, even, or neither odd nor even. That would be number 3. That would be number 3. Okay. So we are going to miss this. Monday is moved to Saturday. Monday is moved to Saturday to give you a 4-day weekend. If Tuesday is free because it's a holiday, then we have a bad habit wanting to rest for several days in a row and not having to come to work at Monday. And therefore Monday is moved to Saturday. But that's not only the university, it's just statewide, it's the government. Government stated that it can be done and it should be done. So probably many private businesses don't do that. But basically it's nice to have 4 free days, so that's why we move Monday to Saturday. And then we have only a 4-day week, Wednesday, Thursday, Friday, Saturday. It's also nice, not so bad. All right, so we are losing 3 lectures. Even with the move, we lose this, and I propose to do something about it. But obviously I cannot force you to come, so we will do something. I'll figure out what to do that would be useful for those who perhaps don't understand things, so perhaps we could do a consultation time for those who are always asking questions. Okay, so number 3, odd or even functions. 3a, is the function odd, even, or nothing? In exercise 3, previous paper, we didn't finish it last time, so we have to rush through it. So, exercise 3 in A, function f of x, x to the 6th minus 4x squared plus 5. Is it odd or even? In 3a, it's even because all the terms have even powers. They will not change signs. B, are you looking at the correct function?
No, neither odd nor even.
Neither odd nor even, because the first 2 terms, x to the 5th and x to the 3rd, are odd functions, but the 3rd is even, so the function will not remain the same, but it will neither will it just change the sign. It will have a completely different value for the opposite x value. C, odd, because it's odd divided by even, so the numerator will change the sign, the denominator will not change the sign, so that's an odd function. D, nothing, it's nothing. It's nothing because the denominator is something that behaves neither in an odd nor an even way. It behaves in an odd way, okay. All of us do. E, it's again nothing. It's again nothing because if you change the sign of x to the opposite, then the value of the function changes. F, it's even because x squared doesn't change the sign, so the function does not. G, sine minus x cubed divided by tangent. Yes, it's even because the denominator is an odd function, the numerator is odd, but if they both change the sign, then the quotient ends up being even without the sign change. H, even because x squared is an even function. G, It's even because cosine function is even.
Yeah.
Alright, so logarithm of the cosine, obviously it's also even. Okay, now graphing. If you finish those graphs so that the functions are even or odd, respectively. So somebody told me that they were trying to find formulas. No need for equations, no need for formulas. So in A, if you are given a graph like this, to make an even function, all you have to do is sketch the missing half. And the missing half, remember the symmetry, opposite x values have the same y values for an even function. An even function is symmetrical with respect to the y-axis. And so that's why you have to simply add the missing half. The same goes for B. The same kind of symmetry. The same goes for C, the same kind of symmetry. In C you would get something like this. In 5 you have to complete each sketch so that the function is odd. How do you do that? That other kind of symmetry. The symmetry with respect to the origin. The central symmetry. So if you are given a graph like this, then to complete this graph so that the function is odd in the end, you must understand that if x changes the sign, then the function simply changes the sign. So for opposite x values, the function values are also opposite. So in number 4, you do the line symmetry, the symmetry with respect to the y-axis. You reflect the given part in the y-axis. You create the mirror image. In number 5, you need the central symmetry, or if you like, the propeller kind of symmetry. You simply imagine, turn the graph 180 degrees around the origin, and you have the complete graph of the odd function. And the last one, which we didn't do, you didn't do, or maybe somebody did. Let's have a look. So there are several conditions for number 6. Several conditions for number 6. So we know that f of x equals minus x minus 1 squared plus 4 for x between 0 and 3. That's one fragment. What's one fragment of the graph is given? Now, well, we also know that the function is actually even, and we know that it's periodic with period equal to 6. So how do we sketch a graph of this function? Okay. So first of all, probably we have to begin with a graph of this. Choose the piece of the graph that we need and see what we can do with it. So how can we sketch this? What kind of function? Quadratic function, the graph is a parabola. Can we find the vertex of this parabola?
1 and 4.
1, 4. Recalling the rule, if the quadratic function is written in this form, then the vertex is at the point Mn. Alright, so it's 1, 4. 1, 2, 3, 4. This is the vertex. Ends down minus square, which means now we can count the squares and it's between 0 and 3. Alright, so it will be 1 right, 1 down, 1 right, 3 down, that's at 3. And of course, because of symmetry, we also have this. So for this, between 0 and 3, we have this fragment of the parabola. There's no need to sketch anymore. There's no need to continue this graph. Because this is between 0 and 3, that's fine. Now, it's even. Because it's even, I know that I have to reflect this part in y-axis to create the other half. So 1, minus 3, 1 something like this. So the first part was create the fragment of the parabola corresponding to x values from 0 to 3. Second part, the function is even, so I must reflect it in y-axis to create the other half of this. And now the period is 6, which means that every 6 units the graph repeats itself. Okay? This is exactly 6 units long, which means that at this point it starts again like this. So if you can do copy-paste with your brain, that's what we have. We take this, we copy and paste. We copy and paste. We copy and paste. So that it's a periodic function. The period is 6 units. And we have an even function to both sides of this. Some people are funny.
Sorry, but I just made the remark that it kind of looks like a bot.
All I can say is everybody sees things according to their own degree of So if that's all that you see there, that's your problem, my dear. That's your problem, that's not mine. I could have chosen another function, of course. One that would be more difficult to graph. I chose quadratic because it's easy to graph and because I wanted to get some shape that's not just this. All right. Composite functions and inverse functions, the next topic. So for calculus, we will need to be able to understand composite functions. And for calculus, we'll also need to be able to find inverse functions. Which means we have to discuss these now because we start calculus quite soon. All right. How do we understand composite functions? Basically, the simplest way to understand this is, let's suppose that y is some function of some variable u, and u is some other function of, well, we might say the variable, for example, x. U is actually u of x, something, or g of x, all right. So the composite function will be expressed in terms of x. So there are two rules, two functions, and we apply the first one of the functions is applied to x, and then the second function is applied to whatever result we get from the first one. In this case, what we might imagine, we have two machines. For example, in one machine we have to drop a coin. The machine spits out some kind of token, and then we can use this token to put it in another machine to get something out of there. So that's a composite function. That's a composite function. If a simple function, we might imagine we drop a coin into a machine and it gives us something. Or we drop a number into the machine and it gives us another number. So the composite function means that we drop a number into the first machine, it gives us another number according to whatever we gave to the first machine. And then we take this number and put it into the second machine and it gives us another number. So that's let's say a popular explanation of composite functions. In practice, it's easy to build composite functions. It's perhaps not so easy to decode the composite functions, but because what's important, what really matters to us, what will matter to us, is which function is on the outside and which function is on the inside, which is the external function, which is the internal function. So generally we write y equals f of g of x. Or we might add some more layers to the onion and put some more functions in there. I always think of these composite functions as onions or cabbages. So if we know x, we can find g of x, and then we can apply the function f to that one. There's another kind of notation. We could write f composition of f and g. This is a circle, a small circle. F circle g of x. And the order of understanding is exactly the same. F is the outer function, g is the inner function. The difference is that the internal function, the inner function, is always applied to x, and the external function is applied to whatever we get by that internal function. So we might say that we always try to understand in what order the operation should be performed. And the last operation is the outer function, and so on and so on. We can move inwards. So, for example, exercise A. So, all right, my example, the first example was, let's suppose f of u is the square root of u, and u of x is, for example, 3x squared plus 1. Then the composite function f of u of x, for example, will be, we put u, the expression for u, instead of u in there, and we get our function like this. If we do it the other way around, if we want to find u of f, then we would need to put the square root of something instead of x. So, as it is, you simply replace the independent variable of the external function by the expression of the internal function. Alright, that's the composite function stuff. Let's just do this exercise A, and then we can move on to exercise B. It's about whatever we can do. I think this should take up all the time for the lecture. Okay, so in A, it's very easy for A because in this case, I still have kept the 1, 2, 3, 4 variables, different variables. So now we have a triple function actually, not a simple composite, but a triple composite consisting of 3 functions, one inside the other. So an onion or a cabbage with 3 or 4 layers, if you like. So in this case, if we have y equals u squared, u equals cube root of v plus 1, and v equals 1 over x, we could start by putting u into the y function and then v into that, or we could start putting v 1 over x into u function and then this expression into the y function. Or if you can do it immediately at once in your head, that's no problem at all. So what do we get here? If v is this, and u is this, and y is this. So the inner function, this is the internal function, the innermost function, because if we want to find the value of y, we cannot find the value of y before we find the value of u. We cannot find the value of u before we find the value of v. So this is the innermost function, this is the next, and this is the external function. So cube root of 1 over x plus 1. Now this is we have put v into the u function, and now to put u function into y means we have to compare this all, just like this.
So that will be in the power of 2/3.
It will be power 2/3, yes. For now, at this moment, we don't really need the power 2/3, but yes, it would be. All right, in B, u cubed, u equals 1 minus v, v equals square root of x. So in B, what should we get? U cubed, all right. Something cubed. Now u is 1 minus v, but v is the square root of x. So at the moment we are simply playing with Lego blocks, building something from Lego blocks. Y equals 2u plus 3, u equals 1 over v, v equals x minus 2 squared. Now what will this be like?
One.
2
See?
u times 1 over v, so u, this is divided by v,
X minus 2.
x minus 2 squared, and
Plus 3.
plus 3, like this, yes, just like this. Or we can simplify, we can of course bring 3 up into the numerator and open the squares and then write it as the quotient of 2 quadratic trinomials. And D, y is square root of u. U is a square of something, and the something, v, is ax plus b. So it's like this. We start by building functions simply because, well, even though what we really need is understanding functions, because when you build functions, it makes it easier for you to unbuild them. So for now, we had some Lego blocks, we put them together to make something slightly more complicated. Now, number 2, going backwards, how do we find the Lego blocks themselves? In number 2, you have some constructions and you have to deconstruct them. Deconstruct them. So if I have the function y equals 1 over x plus 1, I would say this is a composite function. Now, which is the inner function, which is the outer function, that remains to be seen. So how can we decompose this into separate blocks?
Y equals 1 divided by x.
Y equals 1 over
Z.
z if we like, and z equals x plus 1. So, which is the external function?
Internal set.
This is the internal function because that's what we need to do first if we want to find the value of the function y. So this is the first operation to perform if we want to find it. So this is the internal function, this is the external function. So we have y depends on z and that depends on x. This is not very nice notation, not exactly polite from the mathematician's point of view, but at least we can understand the sequence of operations and of this composition. B, all right, cube root of x squared minus 2x minus 8. There are possibilities. There are possibilities.
Y equals to
So y could be cube root of u, for example, and u is
X minus 2
x
into
squared.
square.
x minus,
No, it can.
no. We can write u equals x squared minus 2x minus 8. That's one possibility. That's the simple one. That's the simple one. But I might do something like this. For example, u is v minus 9. V is x minus 1 squared. Something like that. I could build something like this. Or I could say, all right, v is w squared and w is x minus 1. I can actually build a function consisting of 4 functions if I want to complicate things. If I want to complicate things. In reality, in practice, we try to find, let's say, the golden mean, the middle root, because for practical purposes, when we need to understand the composite functions, we need to understand them for basically for differentiation and integration. If I try to split them into tiny pieces, then it's as difficult to understand as it is when we don't split them at all. So in general, we try to find the best root, and in this case, because we are quite good, I assume, with quadratic functions, 2 functions would be enough. The cube root and the quadratic function would be enough. But if we like, we could do this. For that, of course, you have to notice that x minus 1 squared is x squared minus 2x plus 1. That's why minus 9 here. So this is the most complicated. This is the most complicated split. And the simplest split would be cube root of u, and u is just this. There are, well, possibilities. Easy? I'm glad. And I was almost ready to be happy because somebody thought it was easy. It's not difficult once you are used to this. When we deal with differentiation, for example, when we start to work out the derivatives, sometimes people cannot really tell the order of composition, what sequence the operation should be performed, and that, of course, provides difficulty for differentiation. So that's why we have to spend this time, unfortunately. Now the next one, y equals 1 over 1 minus x squared. I think could be 3. Could be 3. So one function could be y equals 1 over u. The second one would be u equals x squared and v equals 1 minus x, for example, like this. For example, like this. Now basically, we could also say that this is, now I'm reminding you of negative exponents. We could remember that this is 1 minus x to the power of minus 2, having a negative exponent. And that would certainly be good for a simpler split. So, for example, y equals u to the power minus 2, u equals 1 minus x. We could do it this way. It will depend on how good you are at composite functions and how good you are at differentiation. For practical purposes, you do what is necessary. And for the same practical purposes, you try to avoid doing the unnecessary things. Y equals minus x squared plus 4x minus 5 and all of it cubed. Well, again, we can do with 2. One function will be cube and the other function will be the quadratic function. The internal function, the external function. So if we use brackets, then it's quite easy to see which function is the internal function, which function is the internal function. Now I'll write another function for you, which is not on the paper, just to make you happy. So sine squared of 3x minus 4. Okay, let's split this one. Because this kind of function is the one that causes difficulties when we begin differentiation at the beginning of calculus. This type of function. Why? Because the 2 after sine, we have to remember that 2, the square, applies to the sine, but not to 3x minus 4. So basically you have to understand that what happens really is sine of 3x minus 4 is squared. The same of, you know what, work here for a couple of years and then you will not say of course when you look at some people. Of course, yes, but at the beginning, when it's important to understand which function is the first one, which is the second one, in what order should we differentiate, for example, the functions, it's important to understand the order. So the internal function would be 3x minus 4 because it's the first thing we need to find if we want to find the value of y. The next function is sine, and the final, the external function is square. It's squared. So actually we can say y equals u squared. U is sine of v, and v is 3x minus 4. So you have to understand the order, even if it's written in some strange order sometimes. I could make it worse. I could put another square here. And then you would wonder what's going on. But the thing is,
much harder
more?
with another square. It's just will be v 3x minus 4 in bracket squares, and we'll get
Yes, you can write it this way. Yes.
letter.
Yes. The thing is, yes. Not too many layers, to keep not too many layers. For that, we need a good understanding of some basic functions. For example, quadratic functions. Quadratic functions, of course, if I put a square here, you wanted to put a square there. It depends on good understanding of quadratic functions. I've seen many, I've seen all kinds of people, all kinds of students. I've seen students who can't get their mind around this. All right, number 3. Composites. F of g, g of f, g of g, g of f of g, and so on. So the situation, we can see that the first 2 exercises, when we did the first 2 exercises, we used different variables to denote different functions. But generally, all functions usually are represented in terms of x. For example, if we have the function f of x equals x squared, alright, g of x equals 1 plus x, I chose the simplest functions possible. I can't think of anything simpler than this. I chose the simplest functions possible, so there we have no f of u and u is v of x, for example. We didn't do that. Instead, we have f of x and g of x, and we have to perform now different combinations, different compositions of these 2 functions, which of which. So, for example, if I start f of g of x, what does this mean? I need to take the g expression and put it instead of x into the f function. So f of g means that instead of x, I have to put this one, f of 1 plus x. But f function means square of whatever we have there. So it's 1 plus x squared.
We are on YouTube.
Okay. Okay. So what we have here is we have to understand that even though we have f of x and g of x, what we actually do is put an expression instead of x, instead of the variable into the function. That's all. What would g of f of x look like? What would g of f of x look like?
We'll get x, we'll get g of x squared.
Yes, but the final, can you tell me the final expression?
X f of x is g x squared, no?
No.
1 plus x squared.
1 plus x squared. The g function is 1 plus x, but instead of x we have to put the x function, the f function.
Okay.
Okay. Actually, we need to practice to get these as quickly as possible. Okay. F of f.
X.
F of f. F function is x squared, and if we apply f function to the result of the f function, it's this. X squared and squared again, so it ends up as x to the fourth. G of g.
2 plus 2,
It's
right?
gonna be 2 plus x.
Just 2 plus x.
Yeah.
Only 2 plus x. G function is 1 plus x, but instead of x we have another g function. So it's 2 plus x. Alright, these were the simple things. Now g of f
So
of
it's
g
second
of...
with
Yes.
okay.
Alright. How do we deal with this one? G of f of g of x.
Make the internal.
Okay, and that will be 1 plus x squared.
Yes, because we have done half of the work already.
Yeah.
This f of g of x, f of g of x is this. We already have it. So we put this
Plus 1.
plus 1. So g is 1 plus x, so it's 1 plus x squared. So if you open the brackets, x squared plus 2x plus 2. Math 2 people, currently many Math 2 people have problems with this. They have a problem with this formula, Math 2 people. So don't be too surprised if I repeat simple things twice. Alright, the next one, GGF. G of f of x.
1 plus 1 plus x squared.
G of f is this one, and g of this will be 1 plus this.
X squared. And then 2 plus
X squared, so it's 2 plus x squared. The next one is g of f of f. In your home task, by the way, your individual homeworks, you know, they will come soon. In your individual home tasks, you will have 3 functions and you will have to build something. Not 2 different functions, but 3 functions and you will have to make different combinations.
No, F.
They're
Same. Why did I write the same thing? G, F, this is F.
And it will be 1 plus x4.
F of F is this, and G is adding 1. So 1 plus this, but this is x to the 4th. And finally, F of G of F of x. Yes.
1 plus x squared squared.
1 plus x squared and squared again. Yes. So it's x to the 4th plus 2x squared plus 1. Okay. Inverse functions. Inverse functions. Well, it would be nice if instead of getting, for example, a can of Coke after I put my coins into the machine, I could put the can of Coke into the machine and get back coins. So that's what the inverse function does, actually. It works exactly in an inverse way. So exactly, we get exactly the same x values from the y values. So it's exactly the same. The definition for the inverse function, of course, is the function g and f. The two functions g and f are inverse if g of f of x is the same as f of g of x and it's x. In other words, if I find the function f of x, then if g is the inverse, it will bring me back from that value back to the original x value. Or the other way around, the order doesn't matter. The order doesn't matter. So the inverse functions, two functions that are mutually inverse, they basically delete each other, delete the consequences each of them provides. Remember inverse matrices? They did exactly the same thing. They did exactly the same thing. So simply the inverse operation. So the given function relates each element of the domain of f into the range of f. The inverse function will take the element from the range of f and make it back into the corresponding exactly that element of the domain of f. And normally in such situations we denote the inverse function not by g of x but f to the power minus 1, but it doesn't mean the power minus 1. Just like with the matrices, we do not call it power minus 1. It's inverse. It's inverse. It's not the power minus 1. You don't write the reciprocal of this function. You don't write 1 divided by f of x. Because the meaning of this notation is inverse function. It's a very specific meaning. It's not 1 over f of x. It's something completely different. All right. How to find inverse functions? How to find inverse functions? We might, first of all, we have to remember if the inverse function is y is f of x, then to find the inverse function to get back to x, starting with y, we have to express x from the formula, whatever the formula is. We have to express x. And then we will have something x is f inverse of y. But the thing is, if we leave it like this, we might say it's still the same relation. It's still the same relation. It's simply x expressed in terms of y, but it's still the same thing. It's as if you take a t-shirt and turn it inside out. It's exactly the same relation between x and y if we leave it like this. To make it into the inverse function really, we also need to exchange the names of the variables. We need to exchange the variables. Because if I write it like this, it's the same relation. Example, y equals x minus 5. So to express x from this, x equals y plus 5. It's the same relation. We simply wrote it differently, but it's exactly the same. So, as I said, the same t-shirt only turned inside out. And if you prefer to wear a t-shirt inside out, no problem. It's still the same. It's still the same. To make it into the inverse function, we do need to exchange x and y. So generally all mutually inverse functions are expressed as y in terms of x. Because if we do not exchange the variables, it means it's still the same relation. Choose any values of x, find the corresponding values of y, and the same will work in this. The same will work in this. This is not a different function. It's the same function, it's simply written differently. And to make the inverse function, we will exchange x and y. And generally, we will do it first, before we even try to rearrange the expressions. So So the plan for finding inverse functions, So first of all, we exchange x and y. So first, exchange x and y. Secondly, we express y from that formula in terms of x. And finally, we need to check the result is a function, because if two different x values have the same y, like in a parabola, for example, in a quadratic function, there are two different x values that give the same y value. How do we find the inverse? We take this y value. Which x value should we give? That's a problem. Yes, change, but which one? So we wouldn't get a function here because, for example, if for 1 and 3 the y value is 2, then for the inverse value, for the inverse function, I should take, all right, let's take 2. What is the inverse function of 2? Is it 1 or is it 3? There's a problem. It's not a function then. And therefore, we need to check that this is a function. This is a function. So we can see that not all functions have inverse functions. We must make sure that the function is one-to-one. In other words, different x values have different y values. Different x values have different y values. This function doesn't have an inverse function, so what now?
So,
Yes.
So does it have an inverse relation?
Yes. We simply cut the domain. We simply, okay, let's delete this part, let's look for the inverse function of this half. Oh, we are not interested in this half, okay, let's look at that part. We look at separate inverse functions. If the function is not one-to-one, we can generally split the domain into parts which are one-to-one and look at each part separately. Sometimes we split it even more. We simply keep a small piece. For example, remember I mentioned that there are not all functions are there in the basic function list. For example, the arcsine, arctangent functions. You might notice, okay, the sine function is like this. So obviously I can't take just, for example, the value 1/2 and ask what the inverse function value of 1/2 is. I would say it's pi over 6, or maybe it's 5 pi over 6, or maybe it's 13 pi over 6, or maybe it's 17 pi over 6. So for the sine function, we actually cut the domain, we cut away the extra parts. We only keep actually half of one period. Not even the whole period, but only half of one period, because in each period of the sine function, the values repeat themselves, and we need to have one-to-one. So the best thing we can do is cut away everything before minus pi half and after pi half. So the sine function, we only keep the sine function between minus pi half and pi half. And then we can find the inverse function. The arcsine values are only between these two, minus pi half and plus pi half. That's an interesting thing. The sine values are only between these two, and the arcsine is defined, of course, only between -1 and 1. So we will talk more about arcsines and arctangents next time, I hope. But the thing is that if the function repeats itself, so periodic functions are very bad for finding inverses. We must always say, okay, find the inverse if x is between this and this. We always need to do something artificially, because those functions where the values are repeated, which are not one-to-one, one x value, one y value, one y value, one x value, those functions would have problems with inverses. Let's do something practically. Okay, real example 1. If the given function is y equals 3x minus 1, let's find the inverse. So the first step, exchange x and y. X equals 3y minus 1. Now the next step, express y in terms of x from this. 3y is x plus 1, so y equals x plus 1 divided by 3. It is 1-to-1 because it's a linear function. The graph of this is a straight line. The graph of this is also a straight line because this is too a linear function. This is 1/3 x plus 1/3. So two straight lines, it is 1-to-1. So basically we... If I move a term to the other side of equality, it changes the sign. It changes the sign. This is actually the operation for which algebra is named algebra. This procedure. So this is the inverse function of this one. The second example, y equals 2 to the power x plus 5. What happens here? First of all, exchange the variables. X equals 2 to the power y plus 4, 5. Now, how to express y from this? Now you need to remember the definition of logarithms. How can we change this?
Logarithm on the base of 2.
Yes. Log to base 2 of which? Of x is equal to y plus 5. Because logarithm actually is the exponent, the index. This is the logarithm value. And from here we can say that y equals log to base 2x minus 5. Minus 5 is not inside the logarithm. So this is the inverse function of the second. Third example. Oh, this is nice. I like this. X minus 3 over 2x plus 5. So to deal with this, we need, of course, we need to exchange x and y. X is y minus 3 to y plus 5. How do we express y from this? What can we do about this one? Practically. Of course, we understand we need to express y is something in terms of x. But in practice, how is that possible? What could we possibly do?
Multiply by 2y plus 5?
Yes, we get rid of the quotient. We multiply both sides by the denominator to get rid of the quotient. So we have x times 2y plus 5 equals y minus 3. Simply multiply by the denominator. Okay, next. If I express y from here, it will still have y inside, so it's not good. I cannot simply move 3 over to that side and say, now I have y equal to whatever. I cannot leave y on the right hand side as well. I can't have y on both sides. We can open the brackets. So it's 2xy plus 5x is y minus 3. Move y to one side and all the terms that do not contain y to the other side. So 2xy minus y equals minus 3 minus 5x. And from here we can express y, of course, if we take the common factor y out of brackets. So I'm reminding you that if I move y to the opposite side, I have to change the sign. If I move 5x to the opposite side, I have to change the sign. Y, common factor outside, 2x minus 1 equals still the same, minus 3 minus 5x. But now I can express y by dividing both sides by 2x minus 1. So it's minus 3 minus 5x divided by 2x minus 1, or any other rearrangement that keeps the correct signs. For example, I could write minus 5x plus 3 on top, 2x minus 1 on the bottom, something like this. For example, if I don't like too many minus signs. Or I could change the signs in the numerator and in the denominator, write this as 1 minus 2x. So 5x plus 3 divided by 1 minus 2x. There are different possibilities. For this, at the moment, we are not going to verify that it's a function. We're not going to verify that it's one-to-one. We will do it next week. We will look at graphing this type of function. This type of function. These are special functions, and they have interesting graphs, and we will look at graphing these functions next week. Well, actually, the graph is familiar. The graph is familiar. It's only might be slightly unexpected what it actually is. And the last example where we have to deal with this function y equals x squared minus 6x plus 1 for x less than or equal to 3. This is the situation where we have a parabola, a quadratic function, the graph is parabola, and to be able to find the correct inverse function, we have to choose to the right of the vertex or to the left of the vertex of the parabola. So for now we are taking to the left of the vertex. Vertex is obviously at x equals 3, minus 3 over 2a, if you remember, to the left of the vertex. All right, so x equals y squared minus 6y plus 1. How do you propose to express y from this one? There are actually two different methods, two different possibilities. One possibility, we can solve a quadratic equation. For example, one possibility, method 1, y squared minus 6y plus 1 minus x equals 0, that's a quadratic equation. The discriminant is 6 squared minus 4 times 1 minus x, which makes it 36 minus 4 plus 4x, it's 32 plus 4x. That's the discriminant. So y would be 6 plus or minus square root of the discriminant, divided by 2 times this, so that's divided by 2. And actually, yes, we can simplify. 6 divided by 2 is 3 plus or minus 2. If I divide by 2, but I want to get it into the square root, it becomes 4. So I have to divide by 4 under the root. So it becomes 8 plus x. And now I can say, okay, if for this function x has to be less than or equal to 3, then for the inverse function, y will be less than or equal to 3, because they are exactly opposite, because they are exactly reversing each other. It means that the range of the given function is the same as the domain of the inverse, and the domain of the given function is the same as the range of the inverse. They simply swap places. So, because I need to have y less than or equal to 3, I need to choose the minus sign. So the final answer will be 3 minus square root of a plus x. That's the less pleasant method. The other one is nicer. But for the other method, you need to recall 9th grade completing the square. I didn't mention it last time, but for the quadratic functions it might be important to be able to complete the square, to separate the perfect square. So for this one, okay, I still have, so method 2. I have x equals y squared minus 6y plus 1. And I will try to separate the perfect square from this. So x equals, if I want a perfect square, instead of 1, what should I have?
3.
No. 3
Plus 4.
9. And then I see, all right, I added 9, I needed to add only 1, so what I do is subtract 9 very quickly and add what was there. So I sort of put something wrong, I am taking it away at once, and I'm putting the correct number. Of course, very quickly people, with just a little practice, people learn to write the correct number at once. But this is how we get the minus 8. So this is now y minus 3 squared, it's this part, minus 8. So now, from this I can write y minus 3 squared equals x plus 8. So y minus 3 equals positive or negative square root of x plus 8, obviously. And y equals, we take minus 3 to the right, it becomes plus, positive. 3 plus or minus square root of x plus 8. And again, remembering this, the final answer will be 3 minus the square root of x plus 8, the same. So you may choose whichever method you prefer. You may solve it like a quadratic equation. Just remember to move x here. It's included in the 3 term because we are solving the quadratic equation with respect to y. Or the other possibility, which I like better because it's, I would say it's neater, it's not so messy, separating the square, completing the square, and of course we need something, we have something remaining, and we move the extra part over to x, and then we take the square root of both sides and move something again. So I would say I prefer this method personally. I understand both, but it's a matter of taste. I like this one better. So right now in these examples we saw how to deal with linear functions. That was easy. Linear functions was easy. Exponential and logarithmic functions. Exponential logarithmic functions might be slightly more difficult until you go home and look up exponential logarithmic functions and review the properties of logarithms and powers. Logarithm rules, power rules, that's something that I take for granted because, well, it's high school stuff. Then, of course, this quotient, the quotient of two linear expressions, linear quotients, in other words, those are, again, the method works where you multiply both sides by the denominator and simplify and express y. Quadratic functions, that's this method. What else theoretically you should know or you should remember, the graphs of two functions that are inverse are always symmetrical. The two graphs are always symmetrical with respect to the bisector of the first and the third quadrant. With respect to this line. So if I have, let's say, the given function, something like this, then its inverse, the graph of its inverse, will be perfectly symmetrical to that graph. So if this is, for example, y equals f of x some function, and this is the y inverse, f inverse, then these two graphs should be perfectly symmetrical. Because for the inverse functions, and the inverse functions, there's always two of them. You can't say, I am a friend, I am your friend, or I am his friend. They're always in pairs, just like inverse matrices. Inverse to what? And so the two inverse functions have graphs symmetrical, and because what is x for one of these functions actually becomes y for the other function. What is y for one of these functions becomes x for the other function. So it's simply as if the axes of coordinates switch places for the graphs, for the inverse graphs. And therefore, we can say that the two graphs are mutually inverse, of the two graphs of mutually inverse functions are symmetrical with respect to the line y equals x, or the bisector of the first and the third quadrant. So, if you know how to graph one of the functions, you can very simply, easily obtain the graph of the inverse. On the other hand, sometimes you don't know how to do this and you can only use this line, this test. You can graph them separately, or you can graph them each of these two graphs, each of these two functions, and check that the symmetry is there. Now, in exercise B1, you have to find the inverse and graph both of them simply to make sure that they are indeed symmetrical. In exercise B2, only find the inverse. Only find the inverse. Okay, we have time, something like 15 minutes. 14, okay. 14 minutes. If you have access to your email, you also have the answers. I put the answers on the third page of this. If you don't have the answers, then I'm perfectly happy to check or help or write the answers on the board or whatever you need. Now, just try finding the inverses.
What do we say the parabola? How it will be reflected?
For x is greater than or equal.
No, I mean just
Okay, for a parabola. Aha. Okay, for a parabola. Okay, let's suppose we have a parabola somewhere. This is the vertex. So to find the inverse, first of all, we need to choose which half of the parabola we take. Normally it's given in the question, or perhaps the real life situation requires that you only use positive x values or something like this. So first of all, you can tell which half of parabola you need because normally it's in the task. It's not just find the inverse function of this quadratic function. The constrictions will always be there. So, okay, let's suppose I choose only this part. And that means, okay, that means that the inverse function will have a graph like this, half of a parabola. Half of a parabola. For example, if we take the function y equals x squared for, let's say, x is greater than or equal to 0, then the inverse function will be the square root function. That's a very simple example. The parabola x squared is this, only for positive x values, and the square root function has the graph this, half of a parabola. But if I want to take the opposite, the negative square root of x, that would mean I have this part of parabola reflected, and that will be this part. So basically, if I choose the whole parabola, if I take the whole parabola, wherever it is, and then I try to reflect it and make something like this, it doesn't work. This is not a function. We have to choose. We have to make sure whether this is the upper part or the lower part. And for that, we need to cut away something from the given parabola. That's why we have to cut away the extra parts from the domain. Because normally, the natural domain quite often does not allow you to find the inverse. And that's why we have this extra condition. Sometimes we take only the values to the right of the vertex. Sometimes we take only the values to the left of the vertex. In this case, x squared minus 4 in C, only non-negative x values. So, not quite like this, because the graph will be somewhat different, but if you plot point by point, it's even easier, because what was y for the first function will be x for the second function, and what was x for the first function will become y for the second function. So plotting point by point is easy, just exchange the coordinates of each point. Okay, the answers minus the graphs are in the email. Why do we change it? Because